law, and this is the basic property of set operation. So I will go through very fast for this session. And commutative law, associative law, and distributive law, the Morgan law, and absorption law. And here are some 10 properties of set operation. These are basic property of set operation. Yeah. First, we have a 5 property of set operation, and commutative law, the example for 2 sets A and B, and associative law, the example for 3 sets, and you can expand for 4 or 5 or K sets also. And later we'll expand the Morgan laws from this example for 2 sets to K sets, A1, A2, and AK sets for to apply the Morgan laws. And next we'll go to computer representation of sets. Suppose that we have a set U. There are n element in the set U, U1, U2, and UN. Each subset M is a subset of U, can be represented by a vector B, B1, B2, and Bn. Bi is 1 if Ui is belong to M. Bi is 0 in other case. And the vector B constructed by this rule is called characteristic vector of the set M. And it's clear that the H subset M belong to the set U correspond to the unique characteristic vector B, and H binary and vector B correspond to the unique subset of U. For example, we suppose that there are 11 elements in the set U, and the elements are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we consider the subsets S and Q belong to the set U. So in this example, S is 2, 3, 5, 7, 11. There are 5 elements in the set S, and all the elements in the set S belong to the all element of the set U. So in this case, S is a subset of U, and the same as Q. There are 4 elements in the set Q, 1, 2, 4, and 11, and all of these 11 belong to the element of the set U. So Q is a subset of U. And if we want to represent by characteristic vector, so you can see that for example, S is a subset of U. There are 5 elements, 2, 3, 5, 7, 11. So in the string of U, 1, 2, 3 until 11, at each position, if the value is appear in from S appear in the U, so the value will be 1. So you can see that there are 5 value 1 in the string at the position corresponding to 2, 3, 5, 7, and 11. And for the other position, we set it to 0. Yeah. So the characteristic vector is 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1. So that is the characteristic vector of the subset S. And you can do the same for Q. So Anyone can answer for the question for the characteristic vector for Q.
Can I answer?
Anyone can find the solution for characteristic vector, the subset Q. And here's the characteristic vector of the subset Q. 1, 2, 4, and 11. So for this position, the value of the characteristic vector will be 1, and for the other position, the value will be set to 0. And please note that all the set of operation, union and intersection and complement can be done by correspondingly logic operation. Here's one example. We suppose that U is a set with 11 elements, 1, 2, 3, 4, 5 until 11. And we consider the subsets S and Q belong to U. And we already know the characteristic vector of two subsets S and Q as in the previous slide. And S union Q, and then we have this value, yeah, S union Q, and S intersection Q, yeah. And how about S complement with Q? Yeah, here's a complement of the set S, and 0 as a position with the value 0, you will set its value to 1. So you can see the set operation, union, intersection, and complement. Do you have any question? I think this is the basic definition of the set. So it's easy for you to understand. I think if you have any question, please let me know. I go a bit fast for this session. Next, we'll go to the subset of enumeration. In many practical problems, we have to examine all the subsets of a given set U. There are n elements U1, U2, and Un. And for example, enumerate of all subsets of U. There are 3 elements, 1, 2, 3. So we have H subsets of U. null 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. Each subset of U is corresponding to a characteristic vector, and enumeration of all the subsets of U correspond to enumeration of all binary n vector. And each binary n vector can be considered as a binary representation of a non-negative integer. And we call it the enumeration of all binary n vector. And the same as the previous example. And enumeration of binary representation for all non-negative integer from 0 to 2 and -1. Yeah. And next we'll go to the list of elements. If the set U contains a larger number of elements, it can be considered as a subset U and have a small cardinality. Binary representation is not reasonable in this case. And here we can represent the subset by the list of all its elements. And the list is usually implemented as the linked list structure. And you can see the example and the section in the data structure subset. And each element of list is a record that consists of two fields, and one of which contains the information of the element, and the other one is a pointer to the next element. And here is one example of the class list node. And this structure can be found in the data structure subset. And we call linked list structure. Next, we'll go to relation. There are 6 types of relation. The first one is an ordered pair, and the second is a Cartesian product. The third one is a binary relation, and next is a relation representation, operation on relation, and property of relation. So there are 6 types of relation. We'll go one by one. And an ordered pair is a set of a pair of subsets with an order associated with them. And in general, the set with 2 elements x and y is different from the set with 2 elements y and x. Because in this case, we consider for the position of the element. X is the first position, is different with x is the second, and y is the first. And 2 order pairs A, B, and C, D are equal if and only if A is equal to C and B is equal to D. And we have an example. If the order pair A, B is equal to 1, 2, then A is 1 and B is 2. And 1, 2 is not equal to the order pair 2, 1. So in the order pair, the order of each element in the set is very important. If you change one of the order or one of the position of the element in the set, so you can find the new set. Yeah. Or we can say that you can find the new pair. And for Cartesian product, for example, you have n sets A1, A2, and AN. Be any set, and a Cartesian product of n sets A1, A2, and AN is defined as below the formula. And each element of the A1, A2, and AN we call an order N2. And if N is 3, we have a triple. And here's an example of set A, and B is a set with 2 elements AB, and C is a set with 2 elements alpha and beta. So we have a Cartesian product of 3 sets A and B and C. Is the formula in this slide. 1, 2, 3, 4, 5, 6. H element. And there are 3 elements in H member. Next, we'll go to the binary relation. Let's A and B two sets, and a binary relation from a set A to a set B is a set of ordered pair A and B, and where A is an element of the set A and B is an element of the set B, and a binary relation from A to B is a subset A, and A is a belong to the A Cartesian product with B. And A relation on a set A is a relation from A to A. And the subset A is a belong to the Cartesian A Cartesian product with A. And please note that when an ordered pair A and B is in a relation A, and there are two ways for you to write the relation A, and it means that an element A is related to element B in the relation A, and Cartesian product A and B and A Cartesian product with A. In this case, A belong to the A Cartesian product with B, and then we call binary relation from A to B. And A belong to the Cartesian product A to A, and we call a relation on a set A. So it's a difference between a binary relation from A to B and a relation on a set A. Here's an example binary relation. Let A be the student in computer science major. There are 4 students. Then both Michael and Ami in set A. Okay. And B is the cost of the department offer. And there are 3 elements in the set B. And we specify the relation A is equal to A Cartesian product with B. And we can see as the set that lists all the students. A belong to the set A and enrolls in the class B belong to the set B. And here we have a specified relation A is A Cartesian product with B. And there are 5 elements in A. We can represent the relation by the graph also. And we can represent the relation in a table as on the slide. It means that we have not only one way to represent the relation by the characteristic vector or by the subset R. We have another way to represent the relation like a graph and like a table. So there are many ways to represent the relation. Depend on your problem and depend on the example. We select the suitable representing relation, a graph or table or characteristic vector or another relation is by subset. And relation on a set. A relation on a set A is a relation from set A to A. And here's the three examples of relation. The first one is R is a relation strictly less than, and the second one is the relation greater or equal, and the last one is the relation strictly greater than. And here are three examples of the relation. And here is another way to represent the relation on a set, and we can represent by a table. And we can show which relation it belongs to the relation R1, R2, R3, R4, R5, R6, and corresponding to the order pair 1, 1, 1, 2, 2, 1, and 1 minus 1, and 2, 2. And it's easy for you to see and understand on the table. And the name of the row is the relation 1, 2, 3, 4, 5, 6, and the name of the column is the order pair 1, 1, 1, 2, 2, 1, 1 minus 1, and 2, 2. So it's easy for you to see the connection and the relation between the R1 to R6 corresponding to or connect to the order pair. Next, we'll go to the relation presentation. There are 6 sets of order pairs: mapping, table, and grid graph, binary matrix, and radical graph. So there are 6 ways for present the relation, but depend on the problem. We select the suitable representation relation. Next, we go to the operation on relation. A relation is a set, and it is a set of order pair if it is a binary relation. And all the set operations apply to relations such as union, intersection, and complementing. For example, the union of the less than and equality or relation of the sets of integer and is the less than or equal to relation of the sets of integer. And the intersection of the less than and less than or equal to relation of the sets of integer is the less than relation of the same sets. And the complement of the less than relation of the sets of integer is greater than or equal to the relation of the same sets. And there are 5 relations: complementary relation, inverse relation, identity relation, and array relation, and composite relation. So there are 5 relations. Next, we'll go to the property of relation. There are 6 property of relation we will study in this session. The first one is the replacive, and the second is the irreplacive, symmetric, asymmetric, and anti-symmetric, and transitive. So there are 6 property of relation. Next, we'll go to some definition and property of function. A function f from a set A to a set B, we denote it by function f A to B, and it's a relation from the set A to the set B, which is satisfied for each element A in a set A. There is an element B in the set B such that AB is in the relation, and if AB and AC are in the relation, then we can see that B is equal to C. And a function is also called a mapping or transformation. In this case, a mapping 1-to-1 or transformation 1-to-1. And the set A in the above definition is called the domain of the function, and B is the codomain. And F is a function if it covers the domain, maps every element of the domain, and it is a single value. And so here is the definition of the function f from a set A to a set B. And please remember that f is a function if it covers the domain and maps every element of the domain, and it is a single value. And single value, it means that each element in the domain is used only once. And in this case, it's not allowed one to many or one to empty. It accepts 1-to-1. And the image of the set S under the function f a to b can be denoted by fs, and fs is the set with all the elements can be denoted by fa, in which a is one element of the set S. And the image of the domain under the function f from A to B denoted by a range f, and range f is fa. And in this case, we can call it the range of f. The example are the following relation also function. Anyone can answer this example, or anyone can explain this example.
Dạ, thưa cô, cái hình 1 là function. Còn hình 2 không phải, tại vì cái 3 từ một giá trị 3 nó sinh ra hai giá trị y là 5 và 8.
Anyone can explain or find the answer for this example. Anyone can find the answer? Anyone can find the solution or can explain? You can see that on the left, you can see that each element of the drone is all of the domain is only used once. So in this case, we call it a function. On the right hand side, tree can be used in twice. Tree is used twice. Connect to the two elements in the other side. So in this case, not a function. So left hand side is a function, but right hand side is not a function because each element in each element connect to the two element or more than two element on the right hand side. So it's not a function. And so you already know the definition of function. Next, we'll go to the property of function. The function f a to b is a function from a set A to a set B. S is belong to A or subset of A, and T is the subset of B. And property 1, f of S union T is equal to Fs union to Ft. And here's the proof for the Fs union T is the subset of Fs union to Ft. And anyone can prove for the Fs union to Ft is a subset of Fs union T. And next is the proof for the Fs union to Ft is a subset of Fs union T. And that's the first property, property 1. And property 2, Fs intersects with T is a subset of Fs intersects with Ft. And here's the proof for the property 2. And next, I will introduce 3 functions: injective, surjective, and bijective function. A function f from a set A to a set B is a set or is called to injective or 1 to 1 if and only if for all elements A1 and A2 belong to the set A, and no two inputs have the same output. And if FA1 is equal to FA2, then A1 is A2. And here's the picture to show an illustration for the injective. No two input have the same output. So you can see that on the left hand side, the function f is not injective because you can see that the two input have the same output is the green color. So two input connect to the one output green color point. But on the right hand side picture, the function is injective because no two input have the same output. So the picture show an illustration of what is the injective function. Yeah. So we can see the difference between the function f is not injective and the function g is injective. So it's easy for you to remember that the no two input have the same output. So in this case, the function called injective 1 to 1. And another function is the injection. The function f a to b is an injection if and only if no two input have the same output. Yeah. So you can see the picture show on the slide. The surjective function f from a set A to a set B is called to surjective. We can say that's on 2. And in the previous function injective, we can call 1 to 1. But in the surjective, we can call on to if and only if every element B belong to the set B, and we can find an element A belong to set A, so that B is equal to the FA. And in this case, F is on to if and only if FA is equal to B, and every output is possible. Can you explain the picture on the slide? Is it a surjective function? On the left-hand side, the function f1 is on 2, means that on the left-hand side, the function is the surjective function. But on the right-hand side, the function g is not on 2. And it is not a surjective function. Yeah, the picture illustrates what is the surjection function. Because a function is a surjective if and only if every element B belongs to the set B. You can find an element A belong to the set A, so that B is equal to the FA. So on the left-hand side, you can find the connection between on the left to the right for all the elements. But on the right-hand side, on the right picture, you cannot find the connection between any element 1, 2, 3, 4 connect to the green element. So the function g is not onto, so it means that it's not surjective function. So this is the picture illustration for the surjection function. A function is called a bijection if it is injective 1-to-1 and surjective onto. It means that it satisfies two conditions. Satisfies the injective function and surjective function. And a function is a bijection if it is a surjective and injective, so it's a satisfied two condition. And in this case, we found that the only exactly one arrow. So the number of elements in the set A is equal to the number of elements in the set B. Here's some example by section. Function can be represented four different ways. The first one is the mapping, and the picture shows the mapping between the element in set A to set B, like a Venn diagram. And the second one can be represented by graph, bipartite graph or pylons or something like another kind of graph, and a table and a matrix. Yeah. So the each function can be represented in some way, and here are four different ways, and depend on your program. You can select the suitable way to represent the function. Mapping, graph, table, and matrix. So that is the all of the definition of set and relation. And the first chapter in the combinatory section. And I know that the set and relation, you already know some basic definition on the high school and the first year. On the first year, so I went a bit faster for set and relation. Next, we'll go to the chapter 1, counting problem. So there are four problems in the combinatoric section. The first one is the counting problem, and the second one is the assistant problem, and the third one is the enumeration problem, and the last one is the combinatorial optimization problem. So there are four basic problems in the combinatorial problem. For the chapter 0 set relation, it means that remind some definition for you to remember. And next we'll go to the first chapter, counting problem. First, I will introduce the basic counting principle, the elementary combinatorial configuration, and the inclusion-exclusion principle, recurrence relation, and generating function. So there are five elements in five contents in this chapter. For the basic counting principle, you know the sum rule. Let us consider two tasks. M1 is the number of ways to do task 1, and M2 is the number of ways to do task 2, the second task. So the tasks are independent of each other. We perform the task 1 does not accomplish task 2, and vice versa. And we have a sum rule. It means that the number of ways that either task 1 or task 2 can be done, but not both. It means that M1 plus M2, and generalized to multiple tasks. There are k things 1, 2, 3 to k, and for each thing we have mi ways. For example, for the first one we have m1 ways to select, and for 2 we have m2 way to select, and k we have mk way to select, and we need to select one of them, m1 plus m2 plus m3 and until mk ways. And the generalized sum rule, if we have a task T1, T2, and Tk that can be done in M1, M2, and Mk way respectively, and any two of these tasks can be done at the same time, then there are M1 plus M2 plus Mk way to do one of these tasks. So we call that it is the sum rule. And the sum rule can also be phrased in terms of the set theory, and the size of the union on K, we need to pair Y disjoint sets in the sum their size. And in this case, we have K sets, A1, A2, and AK be disjoint sets. Then the number of ways to select any element from one of these sets as follows. The number A1 union to A2 and union to AK is equal to the number of A1 plus the number of A2 plus the number of AK. Yeah. So that's the sum rule can be expanded for K set, not only 2 set, but we can expand for K set. And please note and remember the size of the union on K finite pairwise disjoint set is the sum of their size. And you can see the red color is correspond to the left hand side of the formula of the last row, and the green color line corresponding to the right hand side of the formula. Here are some examples for the sum rule. The first one, a student can select a computer project from one of three lists, and the three lists contain 23, 15, and 19 possible projects respectively. And how many possible projects are there to select from? So in this case, we have a 23 plus 15 plus 19. Because three lists are separately, so the total way to select possible project can be sum of all the separate way, 23 plus 15 plus 19. And another example, how many strings of 4 decimal digits have exactly 3 digits that are 9? And you can see that the string can have 4 ways. The first one is the none I as the first digit. Yeah, it's 999, or the none 9 as the second digit, and the none 9 value as the third digit, and the none 9 value as the fourth digit. So with the sum rule, for each of those cases, there are 9 possible for the none value. And for the first digit, it cannot be 0. So in this case, for all these cases, we have the answer is 9 plus 9 plus 9 plus 9 is 36. And next we'll go to the product rule. We consider 2 tasks. M1 is the number of ways to do the task 1, and M2 is the number of ways to do the task 2. And tasks are independent of each other. And we need to perform task 1 thus accomplish task 2 and vice versa. And in the product rule, the number of ways that both task 1 and 2 can be done in M1 multiple M2. And we can generalize for multi-task, means such as task 1, task 2, and task K. And here's the product rule for M task. If each element AI on the K tube, A1, A2, and AK has MI number of ways to select, then the number of tubes can be generated in the product of these MY multiple M2 and multiple MK. And in some counting problem, it's only after building the first element, and we just know how to build the second element. And after building and selecting for the first two elements, we know how to select the third element. And in this case, we use the general product rule, and we suppose construct a K2, A1, A2, and AK by select each element in turn, and A1 can be chosen by M1 way. And after A1 is selected, A2 can be selected by MA way. And the same for A1, A2, and AK minus 1 are chosen. And AK can be chosen by MK ways. Then the number of K2 can be generated by M1 multiple M2 and multiple MK. So in the product rule, we can explain for not only two sets, but also for the case set, and it appears in a lot of counting problem. The example, there are 6 people are competing for 4 prize, and how many different ways possible? The number of ways for tube, first prize and second prize, third prize, fourth prize. Yeah. The second example, there are 18 math major and 325 computer science major. And how many ways are there to pick one math major and one computer science major? In this case, it means that we have to select two, one each element combined with two, one from math major and the other from computer science major. And the total weight is 18 multiple with 325. The next example, the formula for the license plate is a 2 letter and 4 digits. How many ways for the license plate with no letter or digit can be repeated? So the first letter, there are 26 ways to select for the first position, and for the second position, there are 25 ways because no letter or no digit can be repeated. So that if you already select one letter for the first position, so for the second position, letter, there are 26 minus 1, it means 25 way to select. And for the 4 digits position, the first one there are 10 way, and you already select one, so means that for the second position you have 10 minus 1, it means that's 9 way to select, and the same as for the third and the fourth. So this formula represents the number of way for represents the license plate. And how many ways for the license plate with repetition allowed? And yeah. So anyone can find the solution for this question. What is the answer for the question B? Yeah, here is the answer. For the first and second letter, so you have a 26 multiple 26 ways. For 4 digits, you have a 10 multiple 10 and multiple 10 multiple 10. And for the question C, same as B but only for and even digits. Okay. And here's the answer. And I think it was very easy for you to understand the example, the sum rule and product rule. But in some real world application, you can find more complex counting problem. So in this case, you have to combine the product rule and the sum rule, and we can solve more interesting and complex problem if we combine product rule and sum rule and some other combinatoric formula. And another example, how many basic variable single letter or single letter plus single digit? Yeah. So in this case, you use or, so single letter or single letter plus single digit. So if and how many way for single letter means that's 26 way, and single letter plus a single digit, single letter means that's 26, and there are 10 way for single digit, 26 multiple 10. But in you have to combine single letter and single letter plus single digit, means that you have to use the rule of sum. Yeah. So 26 plus 26 multiple 10. And how many integer from 1 to 999 do not have any repeated digits? How many integer from 1 to 999 do not have any repeated digit? And here is the answer. I think it's easy for you to understand. So you partition set A into three sets. A1 is a one-digit integer which have not repeated digit, and A2 is a two-digit and integer not having repeated digit, and A3 is a three-digit integer not having repeated digit. Next, we'll go to elementary combinatorial configuration. Permutation. A pin is defined as a sequence of any four digits from the set 0, 1 to 9, 0, 1, 2, 3, 4 until 9. So the question is how many different pins are possible if repetition are allowed? Anyone can find the answer for this question?
Can you hear me?
Now I can hear you.
10 power 4.
Oh, yes. Thank you. What is your name?
Trinh.
I show full screen, so I cannot see how many students are there in the class, and I cannot see your name. Yeah, sorry. Thank you for your answer. Yeah. Trinh, yeah. We can select a pin based on four-step operation. The first step is we select the first symbol. So there are 10 different ways, and the same as the four step 2, 3, 4. Because in this case, each element can be repeated, and so the answer is the same as the Chin's answer. So thank you. The next question, how many different pins are possible if repetition are not allowed? Chin?
Yes.
Chin's again. Yeah, so there are 10 different ways for the first symbol, and 9 different ways for the second symbol, and 7 for the third and the fourth. And so in this case, we can use the product rule. So the number of ways is 10 multiple 9 multiple 8 and 7. And thank you. And so a permutation of a set A of an object is an order arrangement of the elements of set A, in which each element appears only once. If A is a set with 3 elements A, B, C, then the permutation of A can be found by A, B, C, A, C, B, B, A, C, and yeah. So there are six configuration for this permutation of set A. So how many permutation of any set with n elements?
N giao thừa.
Yeah. So for A is a set with 3 elements, so you can find six configuration. For the first position, you can find how many ways to select, and the second and the third. So you can expand for the generalization with n element. So in this case, here is the number permutation. Yeah, I think that's all of the lecture today. Do you have any question? Do you have any question?
Cô nghe thấy em không ạ?
Yes.
Cô ơi, cô có thể post slide của buổi trước và buổi hôm nay lên Teams được không ạ?
Yes, but for the previous lecture is only remind to you for some definition. The lecture will start from today. The first chapter, yeah, counting problem is the first chapter. In the last week, we remind some definition and notation only. Yeah. So no worry. Do you have any other question? Oh, I found that some students post answer on the chat window, but I could not see the chat window because I show full screen for the slide. Thanks for all of you. You are very active. I think I will send slide once we complete a chapter. Yeah, I will summarize all the definition and example once we finish a chapter and send via the team for all of you. Is okay? If you have a question, please send me an email. So see you next week.
Bye. Goodbye, sir.
Yeah, bye bye. Quân Huy Sang, Trinh, Đinh Thị Kiều Trinh, Duy, Đăng, Thái, Khánh Linh, Biên, Tuấn, Khánh Linh. See you next week.